In this example, we are going to decrypt this coded message here that was encoded using the affine cipher. And it uses the affine cipher where the ciphertext is equal to 17 times the plain text plus 12, and of course modulo 26. 17 here is our factor of A, which is our multiple. And of course 12 here is the shift. So to decrypt this, the decryption for the affine cipher is the plain text is congruent to the inverse of A. So that's A inverse. And then that's multiplied to the ciphertext minus the shift. And of course, that's all going to be modulo 26. But before we can use this decryption here, we have to determine what the inverse is for 17 modulo 26. So the first thing we have to determine is if the greatest common divisor, don't forget the greatest common divisor for A and its modulus has got to equal to 1. So the greatest common divisor for 17 and 26 is indeed equal to 1. 17 is a prime number, and there are no divisors between 17 and 26 except for 1. Now in our table here, our chart here, for all the numerals here, you'll notice that not every number here is going to have a greatest common divisor of 1 modulo 26. So for example, 0 here, the greatest common divisor between 0 and 26 is 26. So that will not have an inverse. The greatest common divisor between 2 and 26 is 2. So this will not have an inverse. The greatest common divisor between 4 and 26 is 2. So this will not have an inverse. And you'll see that all the even numbers here will not have an inverse mod 26. Also 13. The greatest common divisor between 13 and 26 is 13. So this will not have an inverse. So the only inverses we have are these values here. So we're going to determine what it is for 17. So as you recall, we use the division algorithm to help us determine that. So we'll say 26, that's equal to 17 times 1 plus 9. We then take the 17 over and the 9 over. 17 is equal to 9 times 1 plus 8. We bring the 9 over and the 8 over. 9 is going to be equal to 8 times 1 plus 1. Since our remainder here matches the greatest common divisor here, we're done. We then write these in terms of the remainder. So we'll write this as 26 plus 17 times negative 1. That's equal to 9. 17 plus 9 times negative 1. That's equal to 8. And then 9 plus 8 times negative 1. That's equal to 1. We then start with this equation here, and we substitute the value for the level before it. So we're going to write this as 9 plus 8. And again, what is 8? 8 is 17 plus 9 times negative 1. And don't forget the negative 1 here. And again, you can check by going ahead and doing the arithmetic. Once we're here, we then distribute. 9 plus 17 times negative 1 plus 9 times negative 1 is 1, so we'll just leave it like that. We then gather up like terms. This becomes 17 times negative 1 plus 9 times 2. That's equal to 1. And notice that this expression here looks like this one here. So we continue. 17 times negative 1 plus 9. 9 equals to 26 plus 17 times negative 1. And don't forget to tag on the 2. We then distribute. 17 times negative 1 plus 26 times 2 plus 17, negative 1 times 2, that's negative 2. Gather up like terms. We now have 26 times 2 plus 17, negative 1 and negative 2, that makes negative 3. Now recall we want to know what it is for modulo 26. So 26 times 2 plus 17 times negative 3 modulo 26, does that equal to 1? 26 mod 26 is 0, and 0 times 2. So if you recall, this cancels. Again, that's by design. So we're left with 17 times negative 3 mod 26. 17 mod 26 is 17. Negative 3 mod 26. Using a practical approach, if we're at negative 3, come all the way back 26, we end up at 23. So we have 17 times 23 mod 26. That does equal to 1. So A times A inverse mod n has got to be equal to 1. So our inverse for 17 mod 26 is 23 mod 26. So our inverse, I'm just going to pen it in right over here, for 17 is 23. Now that we know the inverse mod 26 for 17, we use that in our decryption formula to decrypt this message here. So let's do that. So I'm just going to rewrite this out here. L P S Z A I Q P C Q F M R X S, and then finally Z and C. L, that's 11. P, that's 15. And we're going to do that for each one of these. Now that we have all the designated numerical equivalents here, we'll go ahead and we will use the decryption code here. So our plain text is going to be congruent to the inverse here, and we determined that the inverse was 23. So that's going to be 23 times our cipher text, that's 11 for L. Minus our shift, which is 12. mod 26. 11 minus 12, that's negative 1. 23 times negative 1, so this is congruent to negative 23, which is congruent to 3 mod 26. And of course, the remainder here, that's now our plain text, and we'll put it right there. For P, same idea. Here's our A inverse. P, which is 15, minus 12, modulo 26. 15 minus 12 is 3. 23 times 3, that's 69. 26 goes into 69 twice, with 17 left over. So the plain text here is 17. For S, we continue. 23, that's our inverse. S is 18 minus 12 modulo 26. 18 minus 12, that's 6. 23 times 6, that's 138. That's congruent to 8 mod 26. So then this is 8. And we continue this all the way down the line. So this would continue as 23, our inverse. Here we have 2 for C. Mod 26. 2 minus 12, that's negative 10. 23 times negative 10, that's congruent to negative 230. Which is congruent to 4 mod 26. So this is 4. Now that we have all the plaintext numerical values, we just go ahead and we put in their letter equivalents. 3, that's D. 17, that's R. 8, that's I. And we do this all the way down. We kind of go ahead and gather up or break up the 5-letter blocks. And our message here is drink more Ovaltine. And there we go.